Oh, this is the next slide. Is that okay?
Yeah, that's working. Yeah, all right.
Okay, sure. Yeah, so I'm ready to start whenever.
Yeah, all right then. So, okay, welcome everybody. So today it's my pleasure to welcome Qianxiao Li, who will be talking about approximation theory for machine learning and dynamical systems. So, thank you.
All right, so thank you, Wendin, for the invitation and organizing this seminar. Before that, can I know how long do I have to talk?
Yeah, I mean, there's no real time limit, so just feel free. I think it's nice to explain.
There's a next speaker at 8.
Yeah. So the next speaker will talk after you. So
yeah, okay, sure. Yeah, so I'll take about around 45 minutes and then.
It's up to you. We can talk.
Questions.
Yeah, we had. We had like speakers for going for 1.5 hours. Yeah, so don't worry.
Oh wow. Okay. Probably won't go for that long. Okay, so I'll start. So today I'm going to talk about some approximation theory questions concerning machine learning and dynamical systems. So this really comes from some motivation about analyzing, for one, these compositional structures that arises in learning algorithms or architectures that we see today, like deep learning. And on the other hand, also it arises from some analysis of dynamical systems using machine learning, like recurrent neural networks and similar architectures. So the origin is a bit different, but you can see that there's some interesting relationship between the theory here. And today I'm only going to talk about approximation theory, but I think that it also involves, although it's like a narrow part about machine learning, it has some interesting things to be discovered, even for very simple settings. And hopefully I'll convince you of that later. So today I will mainly talk about 3 kinds of approximation theory. One is for residual networks, which you can think about as approximation theory for compositional function approximation. And then for the next 2 parts, I will talk about approximation theory for learning dynamical relationships with first RNNs, recurrent neural networks, and also more recently there's some interest in doing using convolutional structures for time series modeling. So hopefully my goal is to use very simple settings, but representative settings, to reveal what's different about many models that's being proposed in the time series modeling literature, at least in the machine learning literature nowadays. Okay, so a little bit of background and motivation. So as you can see, deep learning and machine learning in general has achieved a lot of practical success, but theoretically, there's still a lot of mysteries. I'm not saying that the entire thing is a total mystery, but there's a lot of interesting questions that waiting to be answered, and we'll see some of that today. And why I'm interested, why one would be interested in resolving these theoretical mysteries is because we were seeing a lot of emerging applications of machine learning in new topics, away from game playing or image processing towards scientific applications, like simulating molecules or predicting phase transitions and whatnot. And you can see this emerging trend, and it's very important, especially coming from someone who studies physics and chemistry to understand, what is this models actually doing, right? So the one key motivation for me is that I want to develop machine learning theory and eventually also applications in this science and engineering domains. So what is the connection of this to dynamical system? I guess I don't have to really convince the interest group here, but you can see that this compositional or dynamical structures arises in various aspects of machine learning. For example, in terms of model, right? So you have this deep neural network. You can think of each layer as representing some transformation of the features. So as you feed your input into a deep neural net and you obtain an output, you can think of this as really a discrete dynamical system. And then, of course, recurrent neural networks, you basically iterate this connection many times, and then there's of course a dynamics by itself. So here you can see that the model has some compositional dynamical structure. And in scientific applications, there's also this dynamical structures that are present in the data. Like, for example, we often work with data that varies in time, and we apply, very often some models that also has this temporal structure to learn some underlying relationship. How do they interact? Is a very interesting phenomenon as well. And the last part, besides model and data, the algorithm we use to train neural networks or machine learning models in general also has a dynamical structure. If you look at the loss function, it kind of moves down, but it has some fluctuations, and very often the dynamics of this training algorithms are also of interest. From a dynamical systems point of view. So Okay, so this slide, I guess I don't have to go through it. It's just saying that, composition of functions is really just dynamics. They can be viewed interchangeably, and it's sometimes useful to view them interchangeably, as we'll see later. So roughly, there are three categories of interactions of this machine learning and dynamics. And of course, this is not only classification, this is just classification I found useful. So the first classification is machine learning via dynamical systems. And you can think of that as using dynamical systems tools or ideas to analyze this new modern phenomena, or like, new models that is very popular in machine learning, right? To understand how they work, why they work, when do they work. So example is, dynamical formulation of deep learning, or, dynamical analysis of learning algorithms, so on and so forth. And then the second category you can think of is machine learning for dynamical systems. So this is where you have some problem that arises from some dynamical situation, right? For example, you have time series forecasting, or you want to classify a sequence, let's say some words into a positive or negative sentiment. These problems involve time series. You can think of this time series processing problems. And we usually have to, design our machine learning algorithm to be able to deal with this kind of dynamical problems. Okay, so this is a very big class of problems. And the last one is machine learning of dynamical systems. So this is slightly different from machine learning for dynamical systems, in that the goal of this kind of problem is really to recover some representation of underlying dynamical system from observation. Like, for example, you just want to learn a mathematical model for this dynamics, or you want to learn some reduced mathematical model. Okay, so you can think of this as a special case of that, but it's a little bit more precise. So today I'm going to mostly talk about the first two categories and some approximation theory. They are interesting, each of them. Okay, so a quick introduction on supervised learning to mainly to throw out the words I'm going to use. So supervised learning, in a nutshell, is learning to make predictions, right? So you have some data set containing inputs and outputs, and you have some target function that maps the inputs to the outputs, right? For example, this function f star will just correctly classify each of these images of these animals. And our goal, of course, is to have to learn or approximate this relationship using some information from a collected data set, right? Of cat and label cat, and pictures of dog and label dog. So how do we do this? The first step to do this is to actually define a hypothesis space. Okay, so hypothesis space H is just a set of functions that is easy to compute, easy to optimize over, that you can represent on a computer. So for example, for linear models, then it's just a linear combination of some fixed basis functions. Neural networks also has a hypothesis space. For example, shallow neural network is just also a linear combination of basis functions, except this basis function has a form of a linear transformation followed by a affine transformation followed by a nonlinear activation. But the only difference between these two is that this basis function is not fixed. So this W and which are called weights, and B is called bias, they are trainable. Okay, and you adapt them to data. So this is kind of an adaptive basis model. And finally, you have this deep neural networks, which is just composition of the shallow architectures. So once you have the hypothesis space defined, then the next goal is to find a good one, right? So learning and approximation really involves on picking out the best, in some sense, which we'll say precisely, F in this hypothesis space, so that it makes similar predictions to F star, right? So then you can use that as the learned model. So we usually do that by empirical risk minimization. So this is where we define some loss function that compares the prediction of our model in the hypothesis space here against the ground truth prediction, the prediction of our underlying model we're trying to learn, which we have access through samples. And then we average this distance through our training set. Okay, so this is usually how we find a so-called best model. But of course, this is not really the best model we're looking for, because we want to be able to make predictions on data we have never seen before, right? It's not just the empirical risk. We're really interested in minimizing the population or the expected risk. Which is just replaces the sum by expectation over the joint distribution of the input and output, input and its corresponding label output. So of course, we don't know this distribution. We only have samples from it. So the thing is, we really want to solve this because this ensures that we can make good predictions, accurate predictions on unseen data coming from the same distribution. But since we do not know what's mu star, we can only solve the ERM. Okay, and of course, the minimizers of this too is going to be different in general. and the gap between them is called the problem of generalization. Okay, so this is some basic concepts, and I want to draw a graph plot to show where some of the mathematical problems that lies in this whole supervised learning setup, which applies to any machine learning model, of course. So the first problem, which is the focus of today's talk, is called the problem of approximation. Okay, you just ask if you have some target function, and then you define hypothesis space, then what is the closest distance between any function in your hypothesis space and the target function? Okay, so this error is called the approximation error, and this is called the best model or the population risk minimizer. So, but this is not the only problem, and I just spent a few minutes to say that this is not the only problem we're interested in, right? So we're interested in other kind of problems as well. For example, even if I tell you have a very good model that's in the hypothesis space that's very close to your target, you don't know how to find it, right? So there's this second problem where we take some initial guess, which is easy, just initialize the model in the hypothesis space, and somehow we have to train, optimize to a learned model that's hopefully closer to the best model than the initial guess. Okay, so this process is called training. But of course, there's a gap between these two. And what is this gap composed of? The first part is called the optimization error. That means because we're solving this optimization problem by very often an approximate iterative algorithm, and when you run the algorithm for a finite number of steps, there's always going to be error, right? So the error here is the optimization error. There's a distance between your learned model and the true empirical risk minimizer. And of course, this minimizer and the best model is also different, right? Because your sample is finite. So this is what we were talking before. The best one that fits your training set might not be the best one overall. So there's another error, this generalization error. And if you look at here, the learned model and the target differ by a combination of these three errors, and each of them pose very interesting mathematical problems. And of course, in mathematics, the approximation error has been studied for a very long time under approximation theory and also harmonic analysis. And then in statistics, mainly we're always looking at the generalization error in terms of sample complexity estimates. And finally, in the field of optimization, this is the error we're interested in. So you can think that this machine learning supervised learning model actually combines these three analysis into one, which is, I think, is quite an interesting avenue. Oh, by the way, if anything is not clear, please feel free to stop me via the chat or just with the mic. Okay, so this talk we're only going to focus on the first, arguably probably the simplest one to deal with, which is the approximation error, and we will want to talk about what is new really when it comes to approximation theory when you involve some compositional structures or dynamical structures. So the first one I want to talk about is a approximation theory for residual neural networks idealized as some continuous dynamical system. Okay, so first of all, what is the problem of approximation? In general, we can frame it as such, right? So given some target function f star in some C space, usually it's called a concept space in machine learning, but you can think of it as just some function space, let's say space of continuous functions. You given some target and some error tolerance epsilon. Okay, the approximation question asks: does there always exist some f tilde in your hypothesis space, so that the difference between this your function f tilde and the ground truth is smaller than this tolerance? Okay, if this holds for any target in this space and also any error tolerance, then in some sense this circle is arbitrarily close to this f star for any arbitrary f star. Then we say that this hypothesis space H possesses the universal approximation property. Okay, or mathematically you can also think of it as dense under this form. So this is a general class of approximation theorem, and for neural networks, of course, this is not a new question. People have investigated this in the 1980s. But here, what's new in terms of in terms of modern deep learning is that can we achieve this universal approximation property using some new ways that's different from taking a large number of linear combinations of basis functions? Okay, you can think of that as, for example, Fourier series is one such example where you take many sines and cosines and you just learn or approximate the coefficients of combination, and then you get, of course, universal approximation. And this is known, hundreds of years ago. But what's new here is that can we do that using composition? Okay, so here, what we're interested in is really the deep residual neural network. So you can think of it as a kind of a discrete dynamical system. So we have input that is fed into many layers. Okay, and then each layer comprises a nonlinear transformation function, which I call fk. So this is the function at each layer. You can think of it as architecture in each layer. And theta k is collectively all the trainable parameters, including the weights and biases of that layer. And then this xk is a so-called residual connection. So this is a deep residual network. Okay, so the interesting mathematical question is really how this actually approximates a function by just repeating this basic units many times. So composition of many of very simple layers together. And the idea that one can investigate this problem mathematically in a convenience setting is the continuum idealization. So in other words, since our goal is to reveal, how this many compositions actually affects composition function approximation, we can try to make this into a infinite depth layer, infinite depth network by thinking of this continuous, this discrete layers as a continuous parameter. So in other words, you kind of zoom out and just view the whole thing as a continuum. Now, I want to stress that this is not some new development in terms of ideas. We have been doing that in sciences all along, right? So if you look at solids, they are discrete at atomic level, but some of the most useful equations in solid mechanics are actually zoomed out version of this, where you treat the whole thing as a continuum and then displacements as fields. And similarly for fluids and using the celebrated Navier-Stokes equation. So here we're going to do the same, is that we take this residual network and then we take this continuum limit as the idealized model. Okay, so now if you take the limit by suitably rescaling this function, then you get a new dynamical system, which is just a system with, you can think of a dynamic system with a control theta t, right? That is your weights at every layer. So this has been proposed, of course, quite some time ago in 2017, and subsequently there's a lot of different kind of theoretical or applied work on that. And our goal today is to study how this kind of dynamics can help us approximate functions, because that's our very goal that we talk about, right? We want to approximate some function. So let's take a look at one example and how it might help us approximate functions. So here I have a kind of a contrived toy example of a classification problem. You can think of this as two different classes of points. And you can see at this configuration, of course, there's no linear, like I cannot draw a line to separate them linearly, right? So this is not linearly separable. And what I'm going to do is to feed these points as initial conditions to a dynamical system, or in the form of an ordinary differential equation. Okay, so these initial conditions at each of these points, and I'm going to drive each of these points under the same equation, and this is like a van der Pol kind of equation. And let's see what happens. So we evolve these points on this equation up to some time t equals 4. And then at this moment, you can see that all the points have been unraveled. And you can just draw a simple line here, which is a linear classifier. And we are able to classify these two classes easily. So in other words, the role of this dynamics is really to rearrange or reposition the domain of this function, so that it becomes a much simpler function to estimate, right? So to approximate, you have just a linear piecewise function at the end. Okay, so this is what's happening, and if we give it some names, this is exactly how compositional dynamics can help approximate functions. You have some initial, this x, which is your input to your function, and of your target is a function that maps x to y. Okay, so how does the dynamical, you can think of it as an idealized ResNet approximate this function. First, we're going to copy the input as an initial condition. Okay, and then we're going to drive this through a dynamical system. Okay, and to obtain an output of this dynamics, which we call it x big T. T is the terminal time. And then to the last output of this dynamics, I'm going to apply a very simple function g to give me a predicted label, and hopefully they're equal. They're similar, and I can make that similar by adjusting either g or also theta t. Okay, so you can see that there's two steps. So it will be good to actually define some terms. Okay, so the first one, we call it the transformational family of functions. It's just all the possible flow maps that can map this initial condition to the terminal condition by changing theta t. Okay, so the definition is basically the mapping between the initial and the final state, such that they respect some differential equation like that, where ft is collected from some set of functions f. Okay, you can see this is a more general way of writing this. And then, of course, at the end, we also have a terminal family. So this is usually a very, this is a very simple family of functions that is on linear functions. You can think of it as the last layer of a neural network. Okay, and the compositional hypothesis space here we're considering is really the composition of this transformational family and the terminal family. Okay, so we can write this here, and you can see that this entire compositional hypothesis space is determined by these two highlighted families. One is sometimes it's called the control family. So it's all the possible functions on the right-hand side of your differential equation. If you pull it back to neural networks, this is really all the possible layer, each layer's weights configuration, so all possible weight configurations. And then, of course, you have your terminal family, which is the last layer. Okay, and your entire hypothesis space is determined by this two. So the natural mathematical question is, what conditions on this f and g are sufficient to induce the universal approximation property on h and g? So so on this hypothesis, I want to mention that this is in some sense a purely mathematical question, because now we really forget about neural networks at all, and just say that this f is a family of driving the flow. Okay, and G is some simple family at the end. If you compose them together, what is the sufficient condition on these families so that you can induce the universal transformation, universal approximation by just evolving through time? Okay, so this is a purely mathematical question, and this has not been, as far as we know, investigated. So in this paper, I will sort of briefly describe the results. We give some sufficient conditions of when this is possible. Okay, so so the answer actually depends on dimension. Okay, in dimension greater than or equal to 2, this is actually always possible under very mild conditions. The universal approximation property holds under some mild condition. The first condition is that your terminal family G, so it's the last layer, has to cover the range of f star. Okay, in some sense, this is needed, right? Because you're composing these layers together, and the last pass range must at least have the same range as f star or includes it. Otherwise, there's no way you can approximate it. And the second one is that the f is restricted affine invariant. That means we roughly require a subset of affine transformations to not change the class of functions. For most neural network that you consider today, this is satisfied. Okay, and the last one is the sort of interesting one. It says that the family of functions driving the flow, if you take the convex hull of it under the topology of compact convergence, as long as it contains a well function. Okay, so what is a well function? Well function is just some function we define that is 0 in some bounded convex set and non-zero elsewhere. Okay, it's a Lipschitz function that's 0 somewhere and non-zero other places. Okay, it looks like a well. Okay, if this convex hull of this f contains such a function, just needs 1, and then these 3 properties together will induce the universal approximation property under flows. Okay, so this is sort of a slightly general result in that we don't really care about what architecture it is, but here is a sufficient condition, and you can check that many architectures we use today actually satisfy these conditions, but also some we don't use today will satisfy this condition. Okay, so I said about I talked about dimension greater than or equal to 2. So the question is, what happens in dimension 1? So as you may guess, in dimension 1, the topology actually induces some constraints on what kind of functions you can represent using a flow. Okay, in dimension 1, if you take the terminal family to be just an identity function, because you don't need to change dimension, so might as well just take it to be an identity function. And then this is only true. So the same theorem with the same conditions is true if you give it an additional assumption that your target function is an increasing function. Okay, but without that, this will not be true. And so all these are sort of a density result, right? So these universal approximation property, you might want to ask, what's next is whether you can tell me which functions are efficiently approximated by this composition or this dynamical structure. And here we give some partial answers. In dimension 1, we can actually compute some rate estimates in terms of the approximation with respect to the time horizon, right? So how long do I need to evolve to get a good approximation? But for dimension greater than or equal to 2, as far as we know, this problem has not been settled. And as also mentioned, there's some interesting connections with the controllability problems in the control theory literature. And I give some references here, but I will not talk too much about this. Is there a question? I hear some sounds. No?
If you go to the previous slide.
Okay, which one? This one?
About the family of functions.
Yeah.
So I can look at it if I interchange the word family with point or position of point. You're talking here about trajectories. And
I'm talking about the flow map.
Yeah, but I can view this in a reduced way to simple dynamics between points.
Yeah. So
okay.
you can think of it as a dynamics between a finite number of points. Here, the way we phrase this is by like infinite number of points. So like all the initial conditions to the final condition, right? So in other words, all of the points have to be moved by the same dynamical system. So that gives you a function, right? So for each initial condition, there's a corresponding terminal condition. Did I understand your comment correctly?
Yes. Now,
yeah, you can think of it as correspondence between points. Yeah, go ahead.
The flow is the dynamics, right?
Yeah, yeah.
Or the dynamics is represented by the flow.
Yeah, so the flow, if you mean like flow means the flow map, right? Then yeah, the flow map is the map that's associated with this dynamics.
Well, when I go from initial situation, initial point or initial family to the terminal, there is a dynamics there as well. I mean,
yeah, so
I'm driven from the initial to the terminal. I need some dynamics to drive me there.
Yeah, so this is the dynamics, right? This is the dynamics, which I can abstract it in terms of this kind of control dynamics.
So at this point, I mean, at this stage, can we learn from the simple situation of points and positions, take results from there to understand now this situation of that you describe with family flow?
I believe so, and some partial results are given by these references. I'm here on controllability, right? So controllability usually talks about points, right? So we have a fixed initial point, and we have a fixed terminal point, and can you construct a flow within my constraints to drive that point, one point to another, right? So this, am I correct to understand that this is what you mean when you talk about points?
I think you are, yeah. Now I have another, yeah, and thank you for that. I have another question about, you go from dimension 1 to dimension bigger than 1, which is 2, and so on and so on. Now, classically, there is big difficulty to go from dimension 2 to 3, okay? So this is for me like a bit news. That,
okay, so maybe I can try to explain what's different about dimension 1 with respect to 2 and 3. Okay, so in dimension 1, if you look at a flow map, so you can think of it as drawing trajectories, right? And then due to the uniqueness of ODE solutions, these trajectories cannot cross. That's clear, right? Because if they cross, then going from that point onwards, then this trajectory is no longer unique from that initial value problem, right?
Yeah.
So since they cannot cross, the flow map has to be an increasing function because it preserves order, right? If you look at one dimension, if the trajectories cannot cross, then if one point is greater than another at initial condition, then under any point of the same flow, they cannot be the order cannot be switched, right? If they switch, they have to cross.
So these are force dynamics. So force dynamics can cross, right?
So if they're under exactly the same, I mean, this is an initial value problem, right? So if they are under the same flow, this flow, no matter what, they cannot cross, right?
But the theta of t is a time-dependent forcing function.
Yeah, it doesn't matter. I mean, theta t, you can just pretend this theta t is absorbed into this ft. It's the uniqueness theorem applies for the time-dependent case.
It's unique, yeah. It's unique with x and theta, I guess. But I mean, in
yeah,
the
yeah,
state space of just x, force dynamics, forced or non-autonomous dynamical systems do not have unique trajectories. So.
Well, yeah, but if it's forced, you force it differently for two different points, then yes. But if the force depends on the current position, or the force is given, right? Here's the common force is applied to all points.
Okay.
Right. So in that case, you cannot cross the trajectory. Yeah. So okay. Back to the intuition is that because the trajectory cannot cross, then the flow map can only be an increasing function. Okay, but in 2 dimensions, the 2 dimension higher, they don't have to cross to exchange positions. Okay, so in other words, homeomorphic maps in 2 dimensions are much bigger class than homeomorphic map in 1 dimension. Yeah, so this is not a new result. This is known mathematically. So for example, people have proved that homomorphism driven by some specific ODEs can have some density properties only in dimensions greater than or equal to 2.
Why think of this as like this is open, I guess, open loop controlled problem? If you have also control over the ODE, why not just think of it as learning an autonomous ODE?
Yeah, so this is the reason why we consider open loop is because this is the current kind of continuum model for residual network is open loop. So we use the same weights for everything, right?
No,
and then of course you make a So it's correct.
It's uncontrolled dynamics with no control, because you're not doing closed loop control. So why not think of it as just uncontrolled instead of open loop controlled?
But in no control means what? You use the autonomous system without this theta t?
Yeah, or theta is just not of t, theta is fixed.
Yeah, so if this is just a function of x, this will be a different kind of model, right? So here you don't have this trainable weights, right? In your system. So the transformation family is just
the trainable weights are not with trainable weights, but trainable weights are not a function of time.
They are a function of x. You were trying to say?
No, they're trainable, but you want to find the weight such that the autonomous flow goes to whatever the classifiable.
Okay, so you mean theta instead of theta t is just theta.
Yeah.
Okay, yeah. Then people have considered this. That's called recurrent neural networks. Is an example of that. So you use the same layer, same weights for every layer, which I will talk about later. Yeah. So yeah, you can use that, and people have used it for different purposes. Recurrent neural is one example. Okay. Any other questions about this result? Okay, so if not, then I didn't intend to talk too much about this. And then next, I will talk about some other approximation problem that can be associated with flows or with dynamics. So the second problem I'll talk about is the approximation theory for learning dynamic relationships using RNNs. Of course, it's not very informative. So what I mean, I want to make it a bit more precise. So supervised learning often is performed on its dynamic setting. And if you're here during the learning interest reading group, you might have seen some of this. So I'm going to be considering problems involving prediction of a time series one time series from another, right? Or just assigning a value to each time series. So for example, price forecasting, you want to forecast the price in the future, or you want to do machine translation. In this case, you're not forecasting this, but you are giving a label or prediction for each sequence of words, and then corresponding sequence. And then, of course, in science and engineering, we often have to learn some response systems. So given some temporal forcing, we had to predict some temporal response. Okay, so what's a common property of this kind of problems that is different from the problem that we talked about before is that each output depends on a sequence of inputs, okay, not just one input. And in other words, the price tomorrow is not only dependent on price today, but it's actually dependent on possibly all the past prices. And machine translation also depends, even in the future. So we need to model really a sequence of input and output relationships. So this offers a very interesting domain where we can study if we apply deep learning on this kind of temporal or sequential data. There's some very interesting interactions between dynamical structures in the model and data that could be of relevance. So to make this precise, in a static setting, we have a function that maps a input space to an output space. So this is your input vector and output vector, and the output is just a function of the input. Right? This is the usual situation. And in a dynamic setting, you can think of the input as a sequence, okay, whether it's discrete or continuous. And an output is also a sequence. And how is the output related to the input? You can think of each output, okay, the time index k, yk, or sequence index k, is actually a functional of the entire input sequence potentially. Okay, so for each output k, there's actually a function, or you can think of this as some operator between x and y. So the goal of supervised learning in a static setting is, of course, to learn one function that maps input to outputs. But in a dynamic setting, we're really learning, approximating a sequence of functionals, or you can think of as learning an operator that between these two. Okay, so some examples of this. So what I said is functional. Like for example, one very common benchmark problem is called the adding problem, where you take your output to be some weighted sum of the input up to the current time. Okay, so this alpha k is some weightage that typically decreases, but may not decrease as time as k increases. So you can then see that for each k, your output is actually some weighted sum of your input. Okay, so similarly, time series forecasting, you can think of it abstractly as the next step, xk plus 1, is just some functional, possibly nonlinear, on the entire sequence up to this time. And sequence to sequence model just says that each point of the sequence may presumably depend on the entire sequence, not just the future, not just the past, but maybe also the future. So for example, for translation tasks, the word will depend on the entire sentence. Okay, so that is sort of the basic mathematical setting we can think of when it comes to model dynamic input-output relationships. And recurrent neural network has been proposed to perform this task, quite a long time ago. So what is a recurrent neural network? Basically, you can think of it as a network that repeatedly applies some one-layer neural net. Okay, this is the simple neural network to some state h. We call it hidden state. Okay, so on a schematic, you have some hidden state that flows through time according to some dynamical system. And then at each time, your input, okay, of your relationship, the input time series, enters the hidden state as an external forcing. And then the output, the predicted output, is just some value that's read off this hidden state h. Okay, and the dynamics, of course, is usually in the classical recurrent network setting, is just some one-layer neural net. So this goes back to the question we raised just now. You can see that this neural nets W and U, they do not depend on K. Okay, so there's no time dependence. This is autonomous. Well, if you forget about this U, of course, this itself is an autonomous system that does not depend on time. Okay, and then in a simple setting, this the prediction is just read off as a linear function of this hidden state. But of course, you can make this a bit more complicated if you wish. So you can observe that this recurrent neural network architecture actually parameterizes a sequence of functions, or you can think of it as functionals, as k varies. Why? Because if you look here, y2 will depend on x0 and x1, but y3 will depend on x2, and of course h2, which also depends on the previous ones, right? So each RNN output is going to depend on a lot of the previous, all of the previous inputs. So this RNN really parameterizes a sequence of functions together, and this domain should grow. So it's useful to think of it as functionals over sequences. So training RNN just amounts to how to adjust these parameters, which is W, U, and C, right? So that this sequence of functionals being parameterized by your recurrent neural network can be as close as possible to your target sequence of functionals that you want to learn. Okay, so this parameterizes a sequence of high-dimensional functions or functionals together, and this is very much like the reverse of the Morris-Wansink formalism in statistical physics. Okay, so if you are familiar with Morris-Wansink formalism, what it does is that we take some Markovian system, let's say Newtonian dynamics, and say that I'm not interested in all of the observables. I only care about, let's say, some collective properties, let's say, temperature and pressure of some air in this room. And then how can I derive a closed equation for those properties? And then Morris-Wansink formalism gives a way to do it by introducing some memory. So the system would no longer be autonomous if you reduce into reduced order. So recurrent neural network, you can think of it as curiously doing exactly the opposite. We start with some fully observed system with memory. So this is your input-output relationship, right? So you only care about the input and output. You observe it totally, but it is a memory. It has a memory structure because why the output doesn't depend on one particular input, but depends on the sequence. And what recurrent neural network does is that I'm going to force this fully observed system into a partially observed one by introducing some hidden states that you don't observe. You only observe some functions of it. And once you introduce the sequence of partial observations, but the nice thing is that this system now becomes Markovian. Okay, so there's really a kind of reverse Morris-Wansink formalism used in approximating functions. So if you have played around with recurrent neural networks, you'll find that empirically it is actually quite sensitive to it's quite tricky to train and to use, because when you try to learn long sequences with large memory, recurrent neural networks usually do not perform very well. This is a well-known fact. Fact that's stated in a lot of literature, but mathematically, as far as we know, there's really no nice explanation of why this is the case. And our goal here is to give some explanation in limited settings. So again, as previously, what we're going to do is to take a continuum approach and idealize this entire dynamical system as this discrete dynamical system by adding some residual connections, and then now we can think of this recurrent neural network as a forced dynamical system. Okay, but the W doesn't depend on time. And what we're going to further do is just throw away the activations and just assume that it's identity activation. So this is going to be a big simplification. Of course, it's maybe oversimplification, but we can still retain some very interesting behavior of real recurrent neural networks using this way. Okay, so the idea is basically the main result is that we can show that efficient approximation happens if and only if there's exponential memory decay. Okay, and if there's no exponential memory decay, then we actually have run into issues. Okay, so let me introduce the theory a bit more in detail so that those statements make a little bit more sense. So mathematically speaking, we're going to consider input-output spaces, of course, a space of functions, right? So here, my input space is just a space of continuous functions vanishing at infinity because they're nice to work with. So these continuous functions are just functions of time. So each of them you can think of as a trajectory. This is the input trajectory. And then the output space, I'm just consider the bounded continuous functions. Okay, so therefore the target functional is just a family of functionals that maps this each x sequence into an output y. Okay, so this is a functional from x to r, where x is the space of continuous functions. Okay, so if in continuous time, the linear RNN dynamics is actually given by this ODE, right? So we already said what it is, and here are the usual names that people use. in machine learning literature. And because this equation is is linear, it's easy to solve, and you can actually solve it. And here you obtain the RNN hypothesis space, which I just want you to focus on this term, which you can think of it as just some function convolved with the input signal. Okay, so this is a linear function because we're considering linear RNN, and this is all that there is to it, to this RNN hypothesis space. And here, one caveat is we're going to only consider this dynamics which are stable. So I'm going to assume that eigenvalues of W have negative real parts. So if you look, this function, this RNN hypothesis, of course, has some structure, right? So what kind of structure does it have? One, each of these functionals in this space is just a continuous linear function. Okay, so this is a convolution, and moreover, it is a causal function. It doesn't depend on future values. And moreover, it is a regular functional in that it doesn't depend on values that are on an arbitrarily small interval. Okay, so in some sense, we don't have the spikes of the dependence. And finally, the family is time homogeneous. If there's no special points in time. If you shift things in time, things do not change. Of course, many of these properties, except the linear part, everything holds for the nonlinear activations as well. So the first result we can show is a converse to this simple observation, in that, in fact, this is all you need in order for you to use RNN to approximate any function. So this is a result. So we take any family of continuous linear causal regular and time homogeneous functionals on X, then we can find a RNN that's as close to it as possible, as you like, uniformly in time and uniformly in X. So the main idea of the proof is just to see that since we have a family of functionals that are linear and it satisfies certain conditions, you can actually show that each of their Riesz representation cannot be independent. So there's a common Riesz representation of this entire space of functionals. And so in fact, you can write this H star X, as long as it satisfies these conditions, as a convolution between your input signal X and a rho. The rho you can think of as a Riesz representation of H, not just for one T, but for all T. Then the recurrent neural network approximation question just reduces to how to approximate this Riesz representation using recurrent neural network of the following form. Because if you recall, in the recurrent neural hypothesis space, this is just you can think of as a convolution kernel of the recurrent neural network applied to the input. Okay, so they are very similar as a general linear functional, and how to approximate any function rho with this will give you the results you want. Okay, so this is the first result, but of course, the more interesting one is when what kind of functions can be efficiently approximated a recurrent neural network, right? So here, we want to stress that not all functionals are equally easy to approximate. Here, on the left-hand side, I give a function that's easy to approximate, and right-hand side is not so easy. So there's two things I want to illustrate with this cartoon. So the left-hand side, you can see one, the input is kind of smooth in time, and the output is also kind of smooth in time. Okay, so there's some regularity in time that's being preserved. So you give it a smooth signal in the input, the output also sort of changes gently. Another property is that if you see that the input actually stops changing after a while, right? And you can see that the output also stops changing after a while, at least the derivative becomes 0. So this basically suggests that the output doesn't really depend too much on the history of the input. Okay, so if the input stops changing, the output also kind of stops changing. On the right-hand side is entirely opposite, right? So you have a smooth input that gives rise to a very non-smooth output. And also when the input has stopped changing, the output is still changing. It means that the output is definitely remembering something from the past input. So we would like to say that the first one, we'll show that the first one is easy to approximate, the second one is not. So for this, we really have to make these notions precise. So how can we make the notion of smoothness and memory precise? What we can do is to take a standard basis in RD, and then take a constant signal, EI, to denote as a constant signal with respect to that basis. So you can think of it as just like flat signals. Okay, I'm just going to give a flat input signal to a recurrent neural network and observe its output. Okay, so we denote this output of a constant signal a flat signal by yi, okay? And the smoothness of my family of functionals is just characterized by the smoothness of this map between t and yt. And the memory or the decay rate is characterized by the decay rate of the derivatives of this y with respect to time. Okay, so exactly as what we said here. Okay, we just look at the action of an input or constant signal. So once we have this definition, we can prove a rate estimate. Okay, there's a lot of stuff to process, but please don't process it. Only two things. One is that the final result. Okay, so the final result basically says that we can have an estimate of how close we can get given a limited number of neurons. So neurons means the number of hidden states. Here, m is that number. Okay, and you can see that the approximation rate actually decreases as you increase m at a rate of this power, 1 over m to the power alpha. Okay, and the alpha is just the smoothest coefficient. So we assume that yi, the output of a constant signal, is sufficiently smooth. Okay, and then one most important thing about this part is that you actually assume that the derivative, right, of your output of your constant signal decays at least exponentially. So exists some beta, e beta t is the exponentially increasing one. If you multiply to it, it still decreases as time goes to infinity. This means that this derivative must decay exponentially. Okay.
Is this
so,
decay? I'm sorry.
Sorry.
Is this decay related to convergence rate?
This decay means that how quickly the dependence on past values decays. I cannot tell whether it's
nothing to do with convergence.
So the right hand, so the last estimate is that you can think of as a convergence rate. That means if you give me a target functional, what is the convergence rate of the error goes to 0 as you increase the number of neurons. So this is the rate. Yeah, so this is the decay rate of your signal. Yeah,
so
of your memory.
we actually need the decay to get that convergence.
Correct. I'll show you a precise result later on to say the other way around. Yeah, so we need a decay rate here. At least our results needs the decay rate, and I will show you why in some sense is necessary. So what I want to say, okay, again, I already said, right, that the dependence on alpha is not new. This is usually what we expect in the approximation theory, but the memory dependence is new. Here, the assumption basically is that the output, the derivatives of this output of constant signal must decay like exponential. Okay, for some positive exponential some rate. Okay, and then so here there's no Curzon dimension in terms of time dimension, right? So d is actually multiplied linear, multiplied to the rate, so it's no exponentiation. But there's a Curzon memory here. Why? Because we assume that this is exponentially decay. Now you might ask, okay, what if there's no exponential decay in my memory? It could very well be there's no exponential decay. So what we can show is that, for example, if we take a decay that's like a power law, where the power is omega and omega goes to 0. So you can think of it as a power law decay that decays slower and slower. Okay, then we can show that under our approximation, to meet error tolerance of epsilon, what we're going to need, number of neurons is going to grow exponentially in epsilon with the rate omega. Okay, so exponentially for a fixed epsilon, it's going to grow at a rate that's exponential in omega. That means when your memory starts to become longer, the number of neurons you require to estimate to make sure that you can approximate it well to some fixed accuracy actually increases exponentially. Okay, so we can call this the Curzon memory. Okay, so now to answer the previous question here, we can actually show something a little bit more precise. We can actually show in some sense, an inverse approximation theorem that says that if we assume that the conditions of the previous one, and we'll go from the opposite. Okay, so here there's a lot of words here, but let me just try to explain what is this theorem here. It basically says the reverse. Assume that your target functional, right, can be efficiently approximated by recurrent neural networks. Okay, then this theorem says that the target functional must have exponential decay. Okay, in memory. So this you can think of it as an inverse approximation theorem or approximation theorem of the Jackson, the Bernstein type. So the original theorem says that if you have decay, we have efficient approximation. here it says that if we have efficient approximation, then the target must have decay. Okay, so in some sense it is necessary. Okay, so basically the result 2 and 3 are analogs of classical approximation theorem results. The first one is called the Jackson type result, which tells you I can tell you approximation rates in terms of smoothness and decay properties. So smoothness is classical and decay is something that's new here. And in the inverse approximation theorem, we can think of it as a Bernstein type theorem. What we show is that we can actually show that there must be decay if you have smoothness and effective approximation. Okay, if your approximation is nice, it must decay. And 2 to 3 together, you can think that we can say that efficient approximation is achieved if and only if the target possesses some exponentially decaying memory structure. Okay, if not, then you can construct cases where the cursor memory will occur. So this, at least in a very limited setting, makes the statement rigorous why recurrent neural network have trouble fitting very long sequences with large memory, long memory structures. And in this paper, we actually provide some, well, not this paper, later I'll show the paper. We provide some numerical estimates of that as well. Okay, so here's what I want to say about RNNs. Are there any questions?
These properties about exponential increase in the amount of memory required, is this more of a property of this linear dynamics class? I mean, if you have a nonlinear dynamics like such as an LSTM, right? This is not.
Yeah, thanks for the question. So that I don't have a definitive answer. My suspicion is probably LSTM has something to resolve part of this issue. But I don't, as far as I know, there's no theory that tells how STM can avoid the cursor memory. But I think, yes, if you introduce some nonlinear structures in the right way, you do have, you might be able to resolve this issue, at least in part. What we showed in a paper is that the simplification that we take the activation to be linear is not crucial at all, because all the rate, the memory kind of estimates, you can see that in the paper, we have some more fine-grained estimates in terms of optimization. And all those hold even if you replace, hold empirically, okay, numerically, even if you replace it by a nonlinear function. So having a nonlinearity itself does not resolve the issue, but maybe having LSTM-like structures could resolve the issue. That's one thing that we're definitely interested in to investigate in the future. So initially, I still have like one new work that I want to talk about, but given the time, I don't know. Should I maybe talk for another 5-10 minutes? And
yeah, just carry on. I think it's
okay. So maybe I'll give you some a bit more recent work on a variant of this problem that I think is quite interesting as well. So the last part I want to talk about is approximation of the theory for convolution structures for this task. Okay, so here's motivated by some recent work, by Google on the so-called WaveNet. Okay, so I'll show you a picture of what it does. But the idea is that essentially you're trying to capture the problem we had before was trying to capture the relationship between input time series and output time series, right? Of course, recurrent neural network is one way to do it, but you can also use other methods. And here in the Google WaveNet, here, which is found to be very good for a lot of audio data, they don't use recurrent neural network. Okay, so what they do is to use a dilated convolution. Okay, so what is dilated convolution? Here, maybe I'll just point to the dilated convolution. This is called a dilated convolution. So you take two signals and you add a dilation L into this convolution, displacement. And of course, by increasing this dilation, you have a different kind of using convolution with a skip in the middle. Okay, so what this Google WaveNet does is to apply dilated convolutions one after another to obtain a prediction time series from the input time series. Okay, so let me show you an example. So the dilation rate used in this is usually a power. So at every layer, I'm going to have higher dilation, so that to give a one-channel example. So let's just look at a picture. So this is your input time series. You can think of it as x1, x2. So this picture is taken from Google. And then the output, you can see that I'm just applying a convolution with a one skip. Okay, then I'm going to apply a convolution with like, you know, a 2 skip. And then I'm going to apply another convolution. And finally, you know, by chaining all this convolution together, I'm going to get from one time series to another time series, right? So if you look at here again, this convolution is still causal. So each of these output points depends on the entire history through this dilated convolution. So one look at this is just say, okay, this is still essentially the same setup, right? You are using a different way to parameterize a sequence of functionals, right? Each of these points are going to depend on the history. And so how is this really different from recurrent neural network? In the practical literature, there's examples where one is better than the other. Some argue that, you know, RNN is better, some argue CNN is better. So our goal is really, since we have a good, simple framework to analyze RNNs, why don't we just use that same framework to try to analyze the CNNs? Okay, so that's our motivation. And if you look at our previous theory, so now a slight change we're going to adopt is that we're going to work in discrete time, but still infinite. So the time index is now in the integers. The reason is because if you do continuous time, there's not a universal way of how to define the size of these kernels and the skips. Okay, so we're going to do it on discrete time, but the previous theory still holds in discrete time with some simple modifications. So in discrete time, we can still consider the same continuous linear. This continuous is not the time continuous; it's the continuous of the function, continuity of the function. So continuous linear causal and time homogeneous functional. Then the same general risk representation tells us that this functional has a common risk representation rho, right? Which we with the same name, but now I added this h to make sure that this rho is just a representation of this family of functions. Okay, so this is your risk representation. And if you recall, recurrent neural network just approximates this risk representation by a sum, right, of the power 4. Before that, we have an exponential, but in a discrete time, this becomes a power. Okay, so this is something that's representing this, approximating this. So what about CNN? It turns out the CNN is exactly the same form. Now your rho hat is your CNN's, you know, kind of risk representation. Where rho hat is now a composition of dilated convolutions. So in the one channel case, you can write it simply as a bunch of filters with dilated convolutions whose dilation increases exponentially every layer. Okay, so that's one example. So now it becomes a very precise mathematical problem. Given any target functional, which one of this is which one of these is easier to approximate the target, right? So then we can hopefully answer this question precisely. So I'm not going to go into the details of how we prove this, but let me just show you how we can arrive at a result, right? So you just think we're going to take a simple case where the filter size, so the size of the convolution of filter is just 2, and there's only one convolution channel. So in this case, the 2-layer CNN is just going to be a one filter, which has 2 weights because L equals to 2, and then you convolve it with this one under a skip. So if you calculate this just gives you a sequence that's just the multiple, right? This one multiplied by this one multiplied by this one, and so on. So there's 4 of them. Now the key observation is that you can actually reshape this output into a 2x2 matrix. And this 2x2 matrix, of course, has a 1x2 and 2x1, 2x1 and 1x2 factorization, which is just these 2 filters. So I'm not really doing anything. However, once you observe this, you can see, okay, what kind of sequences can this CNN represent? Precisely, you can represent any 2x2 matrix, right, so with rank 1, right? So this is a rank 1 factorization, and all these weights are arbitrary. So of course, you can represent any rank 1 matrix. And so that means that if we have a target that with support 4, so it only has 4 non-zero values, and it can be reshaped into a rank 1 matrix, then we have perfect representation. So our CNN can represent that precisely. Now, if it's not rank 1, then the approximation error can be calculated by the best rank 1 approximation, right? So in this case, you can just take SVD. We know that the usual SVD analysis tells us that the best rank 1 approximation is just the first principal vector. So we know what is the approximation error. That's just the second singular value. Now, we can take this and generalize it to arbitrary dimensions. Okay, so here's the idea of how we can approximate any signal with this wavelet CNN. first we're going to cut off the signal because the wavenet is always finite support. Support is just L to the power K, where L is the filter size and K is number of layers, right? So this is exponentially increasing because as you stack more layers, the receptive field is exponentially increasing. So first, for any target representation of the functional, we're going to cut it off. And then in the cutoff part, I'm going to tensorize it into a tensor. Okay, so just now that example, row 0, 1, 2, 3, I'm just going to arrange it into a matrix. But let's say if you have 2 times the size, so this is 1, 2, 3, 4, all the way to 7, and then we have to arrange it into a ranked dimension 3 tensor, right? So now you have like a higher order matrix, and of course you have a longer sequence, you have a higher order tensor that I cannot draw here in 3 dimensions. But the idea is that we can tensorize them. And once you tensorize them, you realize that if I have a M channel, depth K, and filter size L wavenet convolutional neural network, then this is the convolutional neural network can precisely represent any rank M tensor. So M is the number of channels. And you can actually write this is tensorization in the following way. So it's the same, similar as what we do here, right? So this tensorization is just this part. So what this tells us is that once we arrange our signals into a tensor, and then what the CNN is really doing is to find a low rank approximation of this tensor. Okay. So in other words, there's really 2 errors when it comes to CNN approximation. The first error is the cutoff error. Okay, once you cut off this, because everything after this signal cannot be approximated by CNNs because CNNs is finite receptive field. And after the cutoff error is discarded, the rest of it is just a low rank approximation error. And this is nice because the cutoff error now, the receptive field actually increases exponentially with that. So maybe this is a way to beat this memory issue because you can actually expand exponentially. Okay, so basically the second part says that low rank approximation is the one that low rank approximation is really the right problem to look at after you take away the tail. So then we need to define some function space that has low rank when you tensorize. So given a sequence, we can define some function some measure, a complexity measure as the following, right? So this is just characterizing the rate of the singular values decay. So if a singular value decays very quickly, then it's easy to approximate by a low rank matrix. Okay, so here this sigma k is just the singular values of this tensorization of my cutoff signal, and then this GS, which converges to 0, is your rate of your decay. Okay, it's the rate of your singular value decay. And I have to say the singular value actually is not the usual singular value because we're talking about tensors. So this is a notion of a higher order singular value. You can see some reference here. So this leads to a function space that tells us that this function space is, you can think of it as a space of functionals whose tensorized singular values decay sufficiently rapidly. So this is kind of a spectral regularity measure that is very similar to smoothness, but not quite the same. So once we have this complexity, we can then prove the result that the approximation rate actually depends on this quantity, how fast it decays. Okay, so if you only look at the upper bound, there's 2 terms to it. The first one is the cutoff error. So this is where you cut off to the L to the K. Of course, this is going to decay exponentially because K is going to be the depth of the CNN. And here, this term G goes to 0. So this term actually decays as you increase K and increase M. M is the number of channels and K is the depth. Okay, so this tells us a precise approximation. It just simply says that if my signal has some spectral regularity of the sense we defined before, you have efficient approximation using CNN. So
what do you mean by spectral regularity? That's
so this just means
eigenvalues?
Yeah, so the singular values of the tensorized, so you have a signal, right? So here, each of your functional, you can represent it by a sequence, right? Because there's a Riesz representation of the functional. Now that sequence, if you shape it together into a tensor like this, right? So if the first 4, you shape it like that, 8, and then you shape it into a 2-dimensional, a 3-dimensional tensor, and then the shape, 16, you shape it into a 4-dimensional tensor. So after you shape it into this tensor, you can talk about the singular values of this tensor. Okay, and if the singular value drops very quickly, then you think of it as a regular. It's very regular. Okay, So the approximation theorem basically says that if you shape it into the tensor, and if the signal falls off rapidly, if the singular values falls off rapidly, then you have efficient approximation, because essentially WaveNet or CNN is just doing a low rank approximation of this tensor. That's what it's trying to do.
You're using singular value.
Yeah.
Is this related to SVD, singular value decomposition?
Yeah. So this reduces the usual singular value decomposition if you consider a ordinary matrix, right? But this is not an ordinary matrix. This is a tensor. It's a higher order matrix, right? So you have to define the singular values. You generalize it somehow. Here we adopt the definition here in this multilinear singular value decomposition. But the main idea is the same. Yeah.
So this is some kind of high
order singular value.
PCA.
Singular value. Sorry.
That's like doing PCA on tensor.
Yeah, something like that. Something like that.
Oh,
yeah, it's similar.
Okay.
Yeah, but except that in PCA on tensor, you have not as nice results as PCA on a matrix, because the PCA on matrix you can show that the rank, the best rank, M approximation is attained by the PCA, right? But here you can only show that the best approximation is upper bounded by the PCA, but it's not tight. Yeah, so the PCA may not be the best possible low rank approximation, but it's a pretty good one.
Okay.
Yeah. So higher order PCA is not as clean. So the Eckhart-Young theorem, which says that the best approximation is just PCA, is not valid for tensor, but it's an upper bound. Yeah. So in other words, yeah, you're right. So here basically the idea is that once we define the decay rate eigenvalues, then the singular values, then we can just use the PCA kind of result to show the approximation rate. So as far as we know, this definition of regularity, which we call it some sort of spectral regularity, is not very well studied. We certainly need to understand a bit more about how such what kind of functions have this regularity. What we can show in the paper here, which will appear soon, is that if you have a sparse signal, so that means your target representation is just sparse. That means your output only depends on few points in the input. Then you have high spectral regularity, so you have efficient approximation. So sparse signals are nice for CNNs, but sparse is not equivalent to this spectral regularity. So that's why there still need to be more investigation. Okay, so maybe to end off, I will just give so the debate, right, in some literature is which one is better, RNN or CNN. Here, the definitive answer for our simple linear model is that neither is better than the other, because we can give an example. For example, if we give a target representation, which is a power law, gamma to the t, then we know that recurrent, not power law, sorry, exponential, right, gamma to the t, so it's exponential in t. Then recurrent neural network with just one hidden unit. So one neuron can give an exact representation, so the error is 0. So this is very good for RNN. But for CNN, you can say that the receptive field needs to be infinite, right? Because you need to increase the depth, and this depth actually diverges so basically you need more and more depth of your CNN to actually approximate this. So this is not very good for CNN. Vice versa, if you take a representation of your target by a constant function, spike at every t to the 2 to the k, t equals to 2 to the k. So you have some spikes that becomes increasingly diffuse. And then in this case, you can show that a CNN, so this is like a spectrally very regular row. And then you can show that a k-layer CNN with one channel per layer can achieve exact representation of this signal. But you can show that to achieve error tolerance epsilon, you can prove this following upper bound, means that the width of the recurrent neural network has to increase exponentially when you increase k. Okay, this is exponential in k, but this is actually linear in k. So in this case, your CNN is going to be much better than your RNN. So therefore, the answer is neither is always better than the other. It really depends on what kind of signals you give it. RNN deals with decaying signals very well, and CNN deals with spectral regular signals, which you can think of as more general than sparsity very well. Like this is a very sparse signal, right? So here we can give some precise answers but in limited settings. Okay, so summary is that we discussed two types of approximation problem involving machine learning and dynamical system. In the first one is about flow map. Okay, so the continuous ResNet maps initial condition to terminal condition. So that's like a flow map. So the flow map can be used to approximate stuff. And the second part, the RNN actually approximates functional relationship by taking an input and output. So you can think of this as like forcing and readout of a dynamical system produces functionals that you can use to represent temporal relationships. So there's two ways you can use dynamical system to do machine learning. And there are, of course, many more. And some generalization we'll be interested in is like, how can we extend the compositional approximation to take into account symmetry, which is very important in scientific applications. And also, the previous result we talked about is always in a linear case. So can we extend it in a nonlinear case? And finally, can we use the same framework to really understand some other temporal methods of learning, for example, in understanding encoder-decoder networks or transformer networks, and hopefully we can make some headway with the mathematical formalism we developed. So with that, let's thank you for your attention. Sorry, I overran pretty badly, but I sort of went a bit slower after knowing that it's okay to overrun a little bit. And if you have any final questions, I'll be happy to answer them. Thank you. So here are the references of the 3 papers. So 2 of which are available online, and this one should be available in a few weeks, I suppose.
All right, thank you very much. Any questions? Maybe like 1 or 2 questions while Soon-Hong, can you start sharing your screen?
Yeah, sure.
Yeah. So there's time for 1 or 2 questions if you want.
Qianxiao, I have one more question about this. This thing you were saying about how CNNs are good for spectrally regular functions and the RNNs are good for memoryless function, I guess, right?
Yeah, rapidly decaying
low memory.
Memory.
Yeah, right. So, I mean, this connects to our recent stuff about doing meta learning for rediscovering Runge-Kuttas, right?
Yeah.
Is it Runge-Kutta sort of has some features of both of these things? It is an RNN, but it's an RNN that takes like this sort of like a at least in the last layer of the in the combining stage of the Runge-Kutta, it's like a dilated convolution.
That's right. That's an interesting observation. Yeah, because it's a convolution of the sum of the previous steps, right? So yeah, I suppose one can ask whether if you take a Runge-Kutta kind of integrator and increase the number of stages, that's kind of like increasing the receptive field of this convolution. But at the same time, you're also iterating it like a recurrent neural network. Yeah, so that's an interesting observation. It could be a combination of these two. Like I'm not sure whether, So maybe that's an interesting point. Yeah, thanks for raising that. I don't have an answer as to what it is, but it's an interesting observation.
All right.
Okay, so yeah, please forward any questions to me if you want, and let's listen to the next talk.
Yeah, okay. Thanks a lot. Thank you very much. Okay, our next speaker is Hoe Lim, who will be talking about noisy recurrent neural networks. Yeah, thank you.
All right, so thank you for the opportunity to speak here. So today I'm going to tell you our recent work on noisy recurrent neural networks. As you can tell from the title, it's going to be involving noise in the model. So this is a joint work with my collaborators from UC Berkeley. So I think like in the previous talk, we mentioned a lot of things about recurrent neural networks. So I don't have to go into the details of what recurrent neural networks are, but just to just in case, let us refresh what they are. So the motivation behind these networks are that we want to be able to deal with sequential data. So we want to be able to learn sequential data. So these data are usually where the order of elements matter, and the elements themselves typically are not independent. And so then so they differ from data without this type of sequential nature. And there are a lot of applications. So for example, sequential data can come in the form of speech, in the context of speech recognitions, or in the context of videos. For example, we want to do video captioning for videos, or in the form of images, where you can basically you can think of like the pixel values in the images as a sequence of pixel values. So recurrent neural networks are specially designed to deal with the sequential nature of such data. So that they are really brain-inspired models that not only gain popularity in machine learning but also in neuroscience. Basically, they are networks of neurons with feedback connections. So this differs from the feed-forward neural networks where there are no feedback connections. And because of this, some people say that arguably they are biologically more possible than other type of adaptive networks. And because of their recurrent nature, they can use their hidden state to process signals that evolve in time, for example. And it can be shown that these types of networks are universal approximators of dynamical systems. And so in many situations, in applications, for example, if you have time series data from some experiment, then you can think of the networks as some sort of open dynamical systems, in the sense that the system is not closed, but it actually interacts with an external signal, right? So it's like it's interacting with another system that destroys the data. So in picture, the networks look like this. And so there's a feedback connections, right, in the network. And you can, the best way to think about this is that you can unroll this network over time, and then you form this type of structures where we feed the input data at each time to the hidden state H here, and then from there you get the output Y. And so another key feature of this network is that you note that the weights, so the W here, right? So WH, WY, and WX, they are shared across time. So it's the same for like for all the time. So this is another key feature of recurrent networks. So today, mostly we are just going to look at supervised learning framework using this type of networks. So the setting is as follows. So let's say that we are given data of the following form. So we have pairs of label data. So XI is input data, and then CI is label or class that correspond to each data. So for example, if you think about regressions, so CI is like some continuous target values. And if you think about classifications, CI correspond to class or the membership. So here, XI, the input data are really input is a sequence. So think about it as a time series, for example. And the learning model here is recurrent neural networks. So here, this is what the standard recurrent neural network would look like. So again, at each time t, right, we are going to feed each element of the sequence, right? So for example, at time t, you feed xt into activation functions A, typically nonlinear, and also it depends on the hidden state. And then also you at each time you get the output functions, but here we are only interested in the output at the terminal time. So after you feed in all the inputs, and then at the end, at the terminal time, you get the output by applying another usually non-linear functions, or typically linear functions G to the hidden state at terminal time. And so simplest example for the activation functions is simply the hyperbolic tangent functions. And here in this example, the parameters are W, the matrices WH, WX, the vectors, bias vectors B, and another matrix WY. that we learn. So all of these we are going to learn as we train the model. So this is just a simplest type of recurrent models that we can think of. There are other variants, possibly with some structure for this type of networks, like equal-state networks, the more famous LSTM, GRU, and then recently there are some new types of architectures like anti-symmetry RNN, fixed RNN, and so on. So there are a lot of works done on deriving new types of architectures for recurrent networks. So all right, so now we have the data, we have the learning model, and to do learning, we need to specify a loss functions that we minimize. So here we just follow empirical list minimization framework. So this is standard setting. And for optimizations, usually we use stochastic gradient descent or maybe some other types of optimizers. And but yeah, stochastic gradient descent is a standard here. So what I show you here is pretty much standard RNN. And I'm going to walk you from so what I call good old RNN, because these are standard and have been known for a long time. So how we can extend this standard RNN to something more modern and something potentially more powerful. So there are two steps here. So first, we recognize that in these update equations for the hidden state H, there are no residual connections or the damping terms sort of. So here we are going to add these residual connections, or sometimes people call it leaky integrator or damping term if you're a physics guy. So so something like this. So there's a term here in the hidden state updates. And then after that, we are going to inject noise into the hidden states. So the simplest example is just simply Gaussian white noise. So then from these equations, we recognize that this is nothing but certain time discretizations of stochastic differential equations. So this is you can think of this as, for example, simply Euler-Maruyama approximations of continuous time stochastic differential equations, SDE. So far we have basically go from the standard discrete time model to continuous time SDE models, and later I'm going to tell you why we prefer to work with continuous time models. So, but for now, let's take these continuous time models as our starting point. So we consider a very general, well, the most general possible SDE. So for the hidden state, and F is what people call drift term here, and sigma is a diffusion term, and B here is Brownian motions. So this is just a standard way to write down SDE. And of course, you can think of this as stochastic analog of ODE or noisy perturbations of the corresponding deterministic systems. And usually these drift terms and diffusion terms are Lipschitz continuous, so that you get assistance and uniqueness of the solutions. So this is a model that we are going to start with, and the output Y is simply just a linear combinations of just a linear transformations of the hidden state. So now I'm going to discuss, so what are the benefits of formulating things in continuous time. So there are 3 point of views that we can take. So the first benefit is that from the design point of view, right? So if we start with something continuous, continuous time models, then we can choose like discretization schemes, right? Just maybe we can choose, Euler scheme or some higher order scheme like Runge-Gutta, and different schemes give you different properties for the resulting models. So it gives us some sense of flexibility when designing recurrent neural networks architectures. And in fact, we can study different stability properties for these architectures. And the second is from the modeling point of view. So think about the case where the input data, right? So the time series, for example. So if they are also generated by continuous time dynamical systems, so these are pretty natural, right? Think about the data that you collect from that they are collected in climate science, so like temperature. So obviously, I mean, temperature evolves in continuous time. It's just that when you collect it at discrete time points, right? So, but really, the temperature comes from some underlying continuous time systems. So, in this sense, yeah, it makes sense to consider learning models that are also continuous in time. And then the third point of view is from analysis point of view, because then we can borrow many tools and techniques from the continuous time theory to do the analysis and potentially gain new, useful insights into these models. So now, so I just introduced you the most general type of SDE as a continuous time model for recurrent networks. So now there are some choices that we need to make when we try to implement it in computer, right? So what are the drift terms and what are the diffusion terms, and like what are the motivations for considering them? So for the drift terms, we are going to write them as a sum of two terms. So the first one is just a linear term, linear in the hidden state, and the second one is a non-linear term. So this is like Lipschitz non-linearity. For example, hyperbolic tangent will do the trick here. And so it also is going to depend on the input data X here. And for the diffusion term, we are going to consider basically combinations of additive and multiplicative noise. So here epsilon is so-called noise level that is supposed to be small because we only want small fluctuations to the system. And sigma 1 is the noise level corresponding to the additive noise, and sigma 2 is the one corresponding to the multiplicative noise. And we made this choice so that we can explore how different values of epsilon, sigma 1, and sigma 2 affect the performance of a network. So this is a very general parametric families of diffusion coefficients. And so during training, the epsilon is positive. So it means that we are going to inject noise during the training. But at inference, so when we apply the network on new test data, new unseen data, we are going to set epsilon equals 0. So in this sense, we can think of training the recurrent network this way as some sort of stochastic learning strategy, because we are injecting noise during training, and then set the noise to 0 when we apply to test data. And later we will see why we do this. Just to give you, just give away the answer is that like doing this can actually help improve robustness of the model with respect to input data perturbations. So think about situations where you have data that are not clean. So in the case of like image classification problems, let's say that people are giving, so instead of clean images, you are given like corrupted images. So these are blur images. And then you still want to do well, right, with these images. So later we will show that by adding, by doing this type of noise injections procedure, by applying this type of strategy, it will help to improve the robustness of the model with respect to such perturbations in data. So anyway, so all right, so we start with continuous time model. We choose the drift terms and the diffusion term, and now we need to discretize the models. So here we just, for simplicity, just consider the simplest type of discretizations that we can consider. So let's just consider Euler-Maruyama approximations, right, to the SDE. So this is the one, and so why not higher order integrators? So the reason, at least for now, for us is that if we use higher order integrators, then the computations are more expensive, and also they are actually not so much of they don't offer much more benefits than using like simple scheme like Euler scheme. So then you had to decide like which scheme to use. So in the end, we go with Euler-Maruyama scheme here. And so yeah, these are just standard assumptions for the SDEs. So now, before I go to the experimental result, I want to provide some theory on so what are the effects of these noise injections, right, on the models. So what are the benefits of the noise in theory? So there's something called implicit regularizations that we can study for this type of networks. So regularizations, you can think of it as like you can think of it as two ways, right? So there are explicit regularizations or implicit regularizations. So explicit regularization is the one that everyone in machine learning is familiar with. So but explicit regularization means that we really modify the loss function explicitly. So for example, we add some terms to the loss functions to enforce certain constraint to the model, right? Something like this. But implicit regularizations, we mean something like we are not really modifying the loss functions, but maybe the loss function is implicitly modified by certain procedure, like training procedure that we use for our models. So this is implicit. And the goal here is that can we understand the benefit of noise by like studying implicit regularizations for noisy recurrent neural networks. So the goal is that if we consider the small noise regime, which is usually the case, right? Because the noise has to be small here. So then we can do some perturbation analysis to derive some approximate explicit regularizer induced by the noise injections. And so this is again the model that we consider, right? Nothing but Euler-Maruyama discretization of the SDE. And epsilon here is assumed to be small parameter. And we want to do perturbation analysis. And so, okay, here there are some notations, but the key quantity here is really the so-called state-to-state Jacobians. So this is like, the derivative respect to the hidden state of the, so of this part here, this deterministic part here. And there's another quantity is, so these state-to-state Jacobians are quantity at a certain time, so at a discrete time, like indexed by m here. So we can also consider products of these Jacobians. So I denote them by phi hat mk. So these are products of these Jacobians like jm and jk. So again, m and k, so they are indexed for the time, discrete time. And so these are the key quantities that we will see, they will pop out later in the explicit regularizer that we derive for the networks. So this is the first main result. So what this result tells us is that we can basically relate the loss functions that we use for training the noisy networks. So we can relate these loss functions, average over realization of the injected noise to that of the, to the loss functions, right, for training deterministic model in this small noise regime. So then we see a formula like this, right? So here we see this epsilon square term here, which is the most interesting one. So okay, pay attention that the terms highlighted in blue are the one that you should pay attention to, because these are the things that I want to highlight. So there are terms Q hat and R hat where they are given by the following formulas. So Q hat and R hat. So the interesting thing here is that not so much about Q hat, but about R hat. So R hat depends on, so again, look at the things that are highlighted in blue. So it depends on the Hessian or the loss functions. And also it depends on the phi hat. So remember, phi hat is, as we said just now, right, is a product of the state-to-state Jacobians. So it depends on this product of state-to-state Jacobians and also the Hessian or the loss functions. And when we compare the relative magnitude of Q hat and R hat, so we can see that Q hat is like is in order of delta square. So delta is the magnitude of the step size. And then R hat is like order of delta. So when the step size is small, R hat is the dominant term here. So when the set size is small, so R hat is a term that we should pay attention to, and in this sense, we can think of the effect of adding noise is to make R hat small, right? So is to make the Hessian or the loss function small and the phi hat small. So this means that injecting noise actually encourage us to encourage the model to find encourage smoother loss landscape or wider minima, and also it encourage more stable models, because these phi hats, I mean the state-to-state Jacobians, right? So they are related to stability of the model. So to summarize, so basically this is what I this is basically what I say, but in alternative point of view, that also we can think of so this like training procedure as some sort of approximation of some type of optimal control problems, where again this epsilon square term here, so this is exactly the same term here, right? Q hat and R hat. So we can see that by injecting noise, we implicitly encouraging more stable models and smoother loss landscape. And in fact, we can see from the plots of the Hessians that when we compare, right, the plots for deterministic model versus noisy models, we see that indeed the loss landscape for the noisy one, so on the figure on the right here, is indeed display smoother landscape than the deterministic model. So this basically confirms that the theory holds. So now we understand what is happening, right? So what are the effects of injecting noise in the network? We want to analyze their effect further in the context of classification tasks. So again, here we follow standard notations that people use in statistical learning. So again, here we are using recurrent neural networks for the classifications, and standard setting, right? We consider so basically we try to minimize cross entropy loss for a classification task, and we use empirical risk minimization framework basically. And the key quantity that we want to look at here are the generalization error, so which is simply the gap between the empirical risk, or well, you can think of it as just a training error, and the true risk, you can think of it as a test error. So we want to see how noise injections basically affect generalization error. Well, to be more precise, the bounds on this generalization error. And also another quantity that we will be interested in is the classification margin. So again, this is a standard definitions that that people use to study this. So the idea is that so what is classification margin? So why we should care about then is that the larger this margin, the more robust the model is with respect to input perturbations. Because you can think of margin as some sort of distance, right, from the network output to the boundary of the classification, to the boundary of the class. So for example, if you have images of cats or dogs, right, there's a hyperplane that separates the region that correspond to cats and dogs. So margin, classification margin is some sort of distance that we can measure from the network output to the boundary, or here, there. So then we ideally want to see a larger classification margin, because then it will tell us that the model is more robust to input perturbations. And so there are some, so here, so this is at the level of the output of the network. And we can also introduce another concept similar to classification margin at the level of the input space, basically. So this is what we call score. And score and classification margin, they are related by, basically simply the network's input-output Jacobian matrix. In fact, you can show the following upper bound that relate the classification margin with the score here. But intuitively, you can think of, again, this classification margin as the quantity that you look at in the output space and the score as a quantity that you look at in the input space, and they're related by the input-output Jacobians of associated to the network. So here, this is the second main result that we have. So here we have basically bounds for classification margin and generalization error for the deterministic networks. And then later I will tell you what are the implications of these bounds. But here goes the result first. So we can basically derive the following lower bounds on the classification margin. So it's lower bounded by gamma, where gamma is a term that's inverse in. So again, look at the terms that are highlighted in blue, right? So gamma is inverse in the two norm of this product or state-to-state Jacobian matrix. So remember just now that we see that what's the effect of the noise is that it implicitly trying to make this small, right? So by adding noise, you want it encourage this term to be small, this two norm to be small. So it means that it encourage gamma to be big. So in this way, you can think of injecting noise as basically making this lower bound bigger. So yeah, so this classification margin bigger, and in this sense, you can think of noise injections as a procedure to make the model more robust to input perturbations. And from this result, we can then derive generalization error bound. So then we can show that with high probability, the following bounds hold. So again, look at the things highlighted in blue. So the idea is that the upper bound for this generalization error is inverse in gamma to k power 2, but the point is that it's inverse in gamma, where gamma is this guy here. So again, when this two norm is small, which is something that the noise injection encourage, gamma is big. So then when gamma is big, this term here is small. So it means that also the upper bound for the generalization error is encouraged to be small by these noise injections. So as a summary, here we see that by looking at these two bounds, noise injections basically favors models with so by doing this by injecting noise, basically we can encourage more robust models behavior, and also models with lower generalization error bound here. And yes, I think this is just what I discussed. Yeah, there are some trade-off in the time step that you use in the noise level, of course, but this is more for the when we look at the experimental part later. So another thing is that we can study the effect of noise from the perspective of stability of a model. So then what we meant by stability, right? So here we take a dynamical system point of view. So in dynamical system theory, right, by stable system, we meant that if we have two trajectories that start close to each other initially, then if they should be able to stay close to each other, right, at subsequent times, right? So this behavior is what we call stable. And for like training recurrent neural networks, it's very important to enforce some stability, right, in both in the model and also in the training. And so in fact, there has been a well-known issue of vanishing and exploding gradient problem. So they have to do with the stability when you do a training for this type of networks. So in the literature, people invented many different ways to enforce some stability behavior. For example, like gradient clipping, or like enforcing some sort of structure in the networks, like LSTM or gated recurrent units. So there are many ways to do this. But the point is that we want to enforce some stability in the model itself. So we want to start with a model that is already stable itself, so that we don't have to worry about what happened later when we do the learning, right? So it's very important to start with something stable. So here, we basically provide some sufficient conditions to guarantee stochastic stability of the continuous time models that we start with, right? So so again, the idea of getting this result is pretty similar to how we would derive such result in the deterministic case. So then again, right, you look at, you have two trajectories. They are slightly perturbed, right, initially, and then you want to see how far away are they, right, at later time. So this is the idea. And here we are going to look at a notion of stability called commercial global exponential stability. So the sense that we actually want the model to be exponentially stable, right? So we want the distance between these two paths actually decreases exponentially over time. So then there's this notion of exponential stability here, so that the system is exponentially stable. So we can basically derive some bounds for sample Lyapunov exponent. So this is the so this quantity here, gamma is lambda. Sorry, is what we define as the Lyapunov exponents. So what we call sample or pathwise Lyapunov exponents. So then we can derive bounds for the Lyapunov exponents of for the hidden state of these networks basically. So then you can see that we can get both upper bound and lower bound, and it depends on the noise levels in these ways. So here you see the sigma 1 and sigma 2 here, right? So again, sigma 1 is the noise level corresponding to the additive noise, and sigma 2 is the noise level corresponding to the multiplicative noise. And so for the bounds, not only that it depends on the noise levels from the additive noise and the multiplicative noise, but it also depends on the spectral properties of this. So A. So remember that this. So our model, right? For the choice of drift term. So A is this guy here in the drift terms, right? Here, and then there's a nonlinear functions here, right? So okay, let's go back. So okay, so it depends on the spectral properties of actually the symmetric part of A, and also depends on spectral property of W. So W is a learnable parameter in the nonlinear term there. And L also depends on the lexic constant of the activation functions that you choose. So then we have this nice bound that will guarantee that the model is stable, exponentially stable, in fact. And so one striking fact about this result is that so by choosing appropriate level of noise, so by tuning like sigma 1 and sigma 2 appropriately, you can stabilize an unstable model. But on the other hand, if you choose, you can choose sigma 1 and sigma 2 to also unstabilize stable models. So you can go both ways. So then for our purpose, of course, we want the models to be stable. So then we have to choose the noise level appropriately to satisfy these bounds so that everything works well during training and so on. And so this is our third main result. So now I think I have finished with the theory part, and next I would like to show you some experimental results that demonstrate the value of adding noise to the recurrent models. So here we consider three tasks actually. So the first two tasks are inspired by MNIST tasks. So the first one is the so-called order pixel by pixel MNIST. So in this task, you sequentially present 784 pixels. So originally, the images are 28 by 28, and you flatten it into a vector of dimensions 784. So you have say 784 pixels, right? So in the first order task, you present these pixels in order to the model, and then in the second so-called permuted pixel by pixel task, you basically perform some type of fixed permutations on these pixel values, and then after that you present it to the model. So then the second task is actually more challenging from the first task, because in the second task the network has to memorize the order of order of permutations as well. So then we are going to apply noisy recurrent neural networks to classify these images, and not just clean images. We are considering different type of perturbations of the images. So in fact, 3 types of data perturbations. So the first type is we are going to add additive white noise to the images. So yeah, just simply add the white noise to each pixel values. And then the second one is salt and pepper perturbations. So this type of perturbations mimics defective pixels. And the last one is the more challenging one, so-called adversarial perturbations, which are worst case perturbations that maximizing certain loss functions subject to certain constraints that we impose. So the last perturbation is is the most challenging one that the network can deal with, basically. And so the result are the following. So for these different types of, so for clean data and also for this noise perturbed or like blur images, right? So then we see that when we compare the performance of our networks, so this RNN is our model, with other state-of-the-art recurrent models, we see that, okay, for the clean data, well, I mean, it's slightly worse than the deterministic counterparts, but only 0.1%, so it's not so much. But the key here is that for the noisy data, right, for blur images, they in fact achieve state-of-the-art performance, as you can see here in the table, right, when we compare the test accuracy right here on test images with the other models. So the first table is the result for the order MNIST task, and similar result, I mean similar behavior can also be obtained for the permuted task. So again, for the clean data, it's slightly worse, but for the noisy data, for the blur images, they again achieve state-of-the-art performance when we compare it with other current architectures. And the same thing here. So yeah, for the last type of perturbations, the worst case perturbations. So again, here we also get superior performance when compared with other models. So here are like basically plots that summarize the experimental result. So again, as we vary the amount of noise, we see that our model is able to deal with the noisy nature of the data. So in the sense that they are robust to the input data perturbations when compared with other models. And yes, so this is for the first two tasks of the order and the permuted MNIST task. So you might think that this is, I mean, they are a bit artificial, but well, I mean, but these are the standard benchmark that people use when comparing different architectures. And then you might wonder, can this type of models do well also on real world data set? So in fact, yes, they can also perform pretty well on real world data set. So here we consider the electrocardiogram ECG classification task. So these are the data obtained by measuring basically signal coming from the heartbeats of a patient that may have severe congestive heart failure. And the idea is that, let's say that in like in real life situations, maybe because there are noise in the measuring process, so the data that you obtained from the patient, they are not perfect, but they might be a bit noisy. And the point is that you want your model to be able to handle the noisy nature of data. So you want them to be more robust with respect to the data perturbations, so that even if there are some measurement errors in the signal, your model can still be able to do really well on these corrupted signals, right? So again, when for this task, again, when compared with other recurrent architectures, our noisy models they do very well on the classification task for the ECG here. So it's basically similar result as an artificial task that we look at here. So just to summarize, so what we have seen in this talk, right? So the idea is that we introduce a new type of recurrent architectures called noisy recurrent neural networks. So the term noisy suggests that we are injecting noise into the hidden state of the networks. And by turning the noise off during inference, we can think of it as some sort of stochastic learning strategy that we show here that they actually improve the robustness of the model against data perturbations. So which is something so this model robustness is actually a topic of high importance in machine learning these days, because you want your model to be resilient, right, to input data perturbations for safety reason or for sensitive applications and so on. So then from theory point of view, so we formulate the model within the framework of SDE. In fact, we start with some model that's continuous in time, and then we choose a discretization scheme. In fact, a very simple discretization scheme, and study the effects of injecting noise using this SDE framework. So we studied implicit regularizations due to the noise injections. So we look at how noise affect classification margins bounds and also generalization error bounds for classification tasks. And then we also study stability of the models in the presence of noise for the models. So this the theory part, and then for the experimental part, we show that so the theory are in agreement with our experiments. So for both artificial tasks and for real world data sets. So we show here that they indeed achieve superior robustness with respect to input perturbations. In fact, they achieve state-of-the-art performance when we compare them to other recurrent architectures. And we believe that this framework, which is very general enough, can be used to guide principal design of reliable and robust recurrent models, at least in the classification case. But extensions to other type of models or other types of settings are possible. And so this is a reference, and you can, if you're interested, you can go into details by checking this paper out. And with that, thank you for your attention.
All right, thank you very much. Any questions?
I got a quick question.
Yeah.
Yeah, thanks for the talk. Here, can you tell us about I know your final estimation actually depends on sigma 1, sigma 2, which in turn depends on the noise level, right? So in general, does the results give a way to pick, in some sense, a optimal noise level to inject? And that's my first question. And the second question is, does it depend on the distribution of the noise? It doesn't seem, you assume it's Gaussian, is it?
Yeah.
Does it depend on the distribution of the noise, or I assume in the small noise limit, it should, right?
Yes. Okay. Okay. Let's start with the second questions first. So yeah, like so here, because we analyze only SDE, right, with Gaussian noise. So then we basically, to derive that result, we borrow some really classical result from the SDE literature, and so then this is how the result looks like, at least in this Gaussian noise case. But for other types of noise, maybe, yeah, I think it's possible to derive like bounds on this, but maybe a dependence on like the sigma 1 and sigma 2, that they might be a bit different, depends on the nature of the noise, right? So for example, if they are non-Gaussian, or maybe if the noise is like has some heavy tail structure, then yeah, I'm not sure like how the bounds would look like. Maybe they will be, yeah, it will be different, I guess.
Okay, but maybe experimentally, do you always inject? I mean, if you inject other kind of noise, does it change the results?
We haven't tried that. So here our model is really like, yeah, simply considering Gaussian noise injections. But the noise to the data, they can be anything like a white noise or adversarial perturbations and so. But the noise in the model is just simply white noise, Gaussian white noise at the moment. But I guess you can also get similar robustness result if you consider other types of noise that they are non-Gaussian, for example.
Okay.
Still
yeah,
get.
actually, I had actually similar, like a related question before going to the other ones. Like, how would you be able to learn like SDEs with bounded noise, for example?
Bounded noise.
Yeah, you just put like an OU process, but the noise is just bounded. I mean, just put
I understand. Yeah, I think it's possible. Because the thing is, yeah, I think maybe I cannot like say for sure because I haven't tried yet. But my intuition is that, yeah, you expect similar type of result. Because the point is here is that you want to inject some sort of randomness into the hidden state of the network to make it robust. And so here we only play with Gaussian white noise because it's the simplest type of noise that we can think of. And also there are a lot of tools that we can use to analyze it. But yeah, I think for bounded noise like OU process, yeah, possible. It's very possible that yeah, you will get similar results.
Yeah, because it just seems that the models you are developing are like sort of I mean, it's nice because the noise is built in the model. I mean, the trainable model. Yeah. Yeah. Anyway, it's good. Yeah. So I think that Qianxiao had the second question, or did you already answer it? Or?
Oh, I haven't answered the first questions of Qianxiao.
Yeah.
Yeah, the question is, does it tell us what kind of strength of noise we should be injecting?
So I think in the experiments we just like simply like handpick like some sensible small level of noise. In fact, we just play around like sigma 1 and sigma 2 values, like the level of additive and multiplicative noise. So like within the bounds, of course, and then we just play around of them, and so we haven't really like optimized like the values of sigma 1 and sigma 2 to get like I don't know some optimal model or something like this. But that could be an interesting direction to look at. But the point here is that like as long as you inject like sufficient, I mean appropriate level of noise, then you could already make the model robust. And then if you want to like quantify how optimal the level of noise is, or like can you like get certain optimal more performance or something, then we need to have some measure of the robustness of the model. So you need to quantify, right, like to quantify the robustness so that you can look at how choosing different values of sigma 1 and sigma 2 will help you to optimize this measure of robustness. But that's interesting thing to look at.
Okay, thank you.
All right, any other questions?
Can we associate noise and uncertainty? Because there are many SDE or stochastic studies that deal with risk and uncertainty. And I have to quote a seminal paper it's called the ADE paper, maybe you know about it, Artsner and Heath, about sub-additive measures, risk measures. Now, when you defined your diffusion early on, maybe in slide 13 or something, you talked about additive and multiplicative, yeah. diffusion equals additive plus multiplicative noise. So I think your wonderful study can focus on understanding this concept of multiplicative, additive, sub-additive, and this can be very rich study.
Yeah, I think like as far as the uncertainty of the model is concerned, I think we are not really like focusing on like uncertainty of the model. Like the goal here is that we want to show that like adding this like random noise can help improve robustness of the model. But yeah, so I think
I think just to add actually to add to Itamar's comment, I mean he made a good comment. Like, if I assume that you are not dealing with an SDE, you are trying to learn random ODE. You have an ODE where we have uncertainty on the parameters, and the parameters are random variables, right? I mean, that could be also a different thing. I mean, it's so yes, just to make his comment more precise. I mean, if you take an ODE with random coefficients, so it's not an SDE, but the ODE itself has random coefficients. I mean,
yeah, I understand. Yeah. Yeah, that could be something interesting to look at. Yeah, random ODE, right? Yeah.
Yeah, it seems like a nice framework. I don't know. Did you answer Itamar's question? Sorry, I just interrupted.
So what's the questions again?
Well, if you could associate the noise is a tool and it's a concept, and there are different forms of noise, but also there is something called uncertainty. And uncertainty in many studies is almost identified with risk. There are risk studies. Okay, so and then you talk about measures of risk. And if you come to talk about measure of risk, and that's related to the question about the noise intensity, the first question here, and then there is a seminal paper that deal with sub-additive risk measures.
Yeah, I of that paper. So maybe you could send me
Artsner. No, there is the simple name is Artsner, and there's 3 other authors, and it's very well known as ADEH paper about sub-additivity. If you Google that, you get that paper. It's a seminal paper.
So can you tell me? So
ADEH. First author is Artsner. I can dig it up and send it to you, of course.
Yeah, please send me. Yeah, send it to me.
Okay, I'll email this to you.
Yeah, thank you. Yeah.
Yeah, all right. Yeah, I was looking, but I found an old thesis by Latch, but yeah, maybe it's something else. All right, then. Any other comments? All right, so I think let's thank both speakers, Qianxiao and Hoe Lim, and for the nice talks. Take care, everyone, and I'm just going to cover on behalf of everyone. Thank you. Yeah, thanks a lot. Take care, everyone. Thanks. Bye.